Let me begin with the introduction of the paper. In recent years, major advances in NLP have been largely fueled by the use of large-scale datasets. However, researchers are increasingly recognizing that small but high-quality data can sometimes be more effective than simply using larger, noisier datasets. Training on massive corpora is also highly expensive, both in terms of time and computational resources. Additionally, when it comes to large language models, we face two major limitations: high latency in API calls and the significant cost of inference. To address these issues, a new trend has emerged: using LLMs as orchestrators that decompose a complex task into smaller subtasks. These subtasks are then handled by smaller, fine-tuned models that are cheaper and faster to run. This orchestration-based approach has created a growing need for compact, domain-specific datasets that can effectively support these lightweight models. As this trend toward task-specific lightweight models continues, high-quality small datasets have become essential for training efficient models tailored to specific domains. One promising solution is dataset distillation, which aims to compress the large dataset into a much smaller, yet equally effective synthetic dataset. Unlike traditional core set selection methods that only pick a subset of real data, dataset distillation actually generates synthetic data that captures the core information of the original dataset. However, applying this idea to text data is particularly challenging because of the discrete nature of language, making it hard to directly optimize or generate synthetic text in the same way we do with images. Some previous approaches have tried to get around this by working with synthetic embeddings instead of text. But those embeddings are often tightly coupled with specific model architectures and tokenizers, which limits their generalizability. So the core question this paper addresses is, how can we perform text dataset distillation in a way that is model independent and widely applicable across different NLP models? To address the challenges of textual dataset distillation, the authors propose a novel three-step method called DALMI, which stands for Data Distillation via LLM Embeddings. The first step is embedding. The input text is encoded into vector representations using powerful pre-trained models like SentenceBERT or OpenAI embeddings. Next is sampling. From these embeddings, a compact subset is selected to retain as much information as possible. This step allows unrestricted search in the embedding space rather than just selecting existing data points. Finally, in the vec2text step, the selected embeddings are translated back into human-readable text using a generation model. The key idea is that the resulting synthetic test is not only compact, but also generalizable across various NLP tasks and model architectures. This paper makes four main contributions. First, it introduces a model-agnostic dataset distillation framework that leverages embeddings from large language models, making it flexible across different architectures. Second, it shows that prompting techniques can significantly enhance the quality of embeddings for task-specific applications. Third, the authors provide empirical evidence that their method achieves strong performance across a range of NLP benchmarks. And finally, the approach demonstrates clear advantages over prior methods in terms of generalization capability and model independence. Now let's briefly look at the related works that form the foundation for this study. There are two main approaches to compressing large datasets for effective training. The first is dataset distillation, which aims to generate a small synthetic dataset that can train a model to perform as well as one trained on the full dataset. This method focuses on learning efficiency, and the synthetic data is not restricted to actual samples from the original set. The second is core set selection, which chooses a subset of real data that maintains the distribution and diversity of the original dataset. Various strategies exist, such as geometry-based, uncertainty-based, or gradient-based sampling. While core set selection works well in many settings, it is limited to existing data points, unlike distillation, which can create entirely new informative examples. Another important area of related work is vector-to-text generation, which focuses on converting embedding vectors back into human-readable text. Early approaches used autoencoders trained on specific datasets, but their applicability was limited. More recently, researchers have developed universal vector-to-text models trained on large-scale corpora, along with multi-step correction strategies that improve the fluency and accuracy of the reconstructed text. This line of work is crucial for embedding-based data distillation, as it enables the synthetic embeddings to be transformed into actual text that can be used across different models and tasks. Now I will move on to the methodology section, where the authors describe their proposed distillation framework. The goal of this study is to perform dataset distillation for textual data. Formally, the objective is to compress a large-scale dataset, denoted as DO, into a much smaller synthetic dataset, DS, where N is much larger than M. Despite the drastic reduction in size, the distilled dataset, DS, should retain the informational context of the original dataset and enable comparable model performance. A key design choice in this work is that both the original and distilled data xi and xj tilde are human-readable text, not embeddings. This allows the distilled data to be easily reused across a wide range of NLP models, regardless of architecture. The paper also provides a formal definition of the distillation objective as shown here. In this equation, theta represents a model trained on a given dataset, and eval is the evaluation function for the downstream task. The goal is to minimize the performance gap between the model trained on the original dataset and the one trained on the distilled dataset. In essence, the motivation is to drastically reduce dataset size while preserving task performance as much as possible. The proposed method is motivated by the idea that LLM-based embeddings contain rich segmentic information and are well suited for manipulation in vector space. By operating in this continuous space, the authors aim to overcome the challenges of directly generating discrete text. The overall framework consists of three main steps. First, text-to-embedding conversion, where raw text is transformed into embedding vectors using a pre-trained language model. Second, synthetic embedding generation, where a small but representative set of embeddings is selected. And finally, embedding to text translation, where the selected embeddings are converted back into readable text using a generation model. The first step is in the proposed method is text-to-embedding conversion. Here, the input text is encoded into dense vector representations using pre-trained language models such as SentenceBERT or OpenAI embeddings. When the goal is task-specific distillation, the authors apply prompting techniques to guide the embedding model toward more relevant representations. This improves the effectiveness of the distilled data for the intended downstream task. On the other hand, when the goal is to create a general purpose dataset, prompting is omitted to ensure broad applicability. The second step is synthetic embedding generation, where the goal is to create a compact and representative subset of the original embeddings. To achieve this, the authors introduce a generator function denoted as GG, which samples embeddings directly from the high-dimensional space. They implement this using k-centroid clustering, which doesn't require training and allows for fast, efficient selection. As an alternative, they also experiment with Gaussian mixture models, but observe similar results. This step enables control over the compression ratio and sampling strategy, making the method adaptable to different requirements. The final step is embedding to text translation, where the selected synthetic embeddings are converted back into readable text. To do this, the authors use text models trained specifically for this task. They adopt a multi-step correction strategy to improve the fluency and fidelity of the generated text. Multiple vector text models are trained, each tailored to specific downstream tasks. This step is crucial because it ensures the distilled data is architecture agnostic and portable, making it usable across various NLP models. As summarized in this flowchart, the proposed framework consists of three main steps: embedding the input text, sampling in the embedding space, and finally converting the selected embeddings back to text. Now I'll move on to the experiments where the authors evaluate the effectiveness of their proposed method. In this experiment, the authors evaluate how the choice of embedding model affects the quality of distilled data. 4 embedding models were used, ranging from Glove 300D to Text Embedding 3 Large from OpenAI, with dimensions from 300 up to 3072. This range was chosen specifically to analyze how embedding dimensionality impacts the effectiveness of distillation. For the Vec2Text model, the authors started from a T5-based architecture and fine-tuned it on embedding to text pairs. The maximum sequence length was set to 128 to prevent degradation in output quality, and BLUE score was used to evaluate reconstruction fidelity. Training continued until the BLUE score converged on the test data. The authors evaluate their distilled datasets on 2 benchmark tasks. First, IMDb, a binary sentiment classification task, and second, AG News, a 4-class topic classification dataset. For downstream models, they use a wide range of architectures. Classical models like logistic regression, naive Bayes, and SVM with TF-IDF features. Neural models like text CNN and text RNN using Glove embeddings, and pre-trained models like DistilBERT and T5 Bayes with their own tokenizers. All models are trained on the distilled datasets and evaluated on the original test sets. Performance is measured using accuracy, and each step is repeated 10 times, reporting the average and standard deviation of it to ensure the robustness. To contextualize the performance of this method, the author compared it against several baselines. First is random sampling, where subsets are randomly selected from the full dataset and evaluated over 10 runs. Second is text dataset distillation, a model-specific approach that generates synthetic matrices rather than readable text. Third, they include easy dataset augmentation, which applies simple textual edits like synonym replacement, insertion, and word swapping. Lastly, deep core is adopted for the vision domain, from the vision domain. It selects core set samples by treating text as a one-dimensional image and applies submodular optimization. While some of these baselines are not directly comparable due to model specificity, they are included to give a broader sense of how the proposed method performs in practice. In the main experiment, the distilled dataset was reduced to just 0.1% of the original data size. The authors evaluated model performance using accuracy, with the full data accuracy serving as the upper bound. The proposed method showed a significant improvement over random sampling across all downstream models. As shown in the table, the proposed method achieves stronger accuracy even with only 0.1% of the original data and consistently outperforms random sampling and EDA. On the IMDb dataset, its performance was slightly lower than TDD by 4.2%, but on AG News, it outperformed TDD by 2.9%. Among all embedding models, text embedding 3 large consistently yielded the best results. This experiment examines how the distillation ratio, defined as the model of the distillation dataset divided by the full dataset, affects model accuracy. As expected, the results show that accuracy consistently increases as the distillation ratio grows. Across all tested ratios, the proposed method outperforms random sampling, EDA, and both GLOVE and E5-based embeddings. Additionally, the choice of embedding model plays a significant role. Text embedding 3 large consistently delivers the best performance, highlighting the importance of embedding quality in the distillation process. To highlight specific results on IMDb dataset, the method was able to recover up to 98.5% of the full data accuracy using just 10% of the data. And on AG News, even with only 1% of the data, the method achieves up to 95.4% of the original performance. These results confirm that the distilled data is highly information dense. Even with a very small portion of the original dataset, it preserves enough signal to support competitive downstream performance. This demonstrates the model's potential for scalable and efficient training, especially in resource-constrained settings. This experiment investigates how the choice of embedding model affects the quality of the distilled dataset. The results show that text embedding ADA002 and especially text embedding 3 large consistently outperforms GLOVE and E5 base. This suggests that higher dimensional embeddings tend to have stronger representational capacity. To further verify this, the authors conducted a linear classifier test. They trained a simple classifier directly on the embeddings to predict the class label. The idea is that higher classification accuracy indicates more useful and informative embeddings. The results confirm that the embedding model quality directly influences the effectiveness of dataset distillation. In short, better embeddings lead to better distilled data and ultimately to stronger downstream performance. In this experiment, the authors examined whether adding task-specific prompts during embedding generation improves distillation quality. They compared distilled datasets generated with and without prompts. The prompts help guide the embedding model to focus on task-relevant features. The results show that task-specific prompts lead to noticeably better performance, especially when using larger embedding models like text embedding 3 large. In contrast, the impact is minimal when using smaller models such as GLOVE or E5 base. The key takeaway is that while prompts are not strictly required, they provide measurable gains. Particularly when using powerful LLM embeddings and when the downstream task is known in advance. This experiment investigates how the quality of vector-to-task model affects the performance of the final distilled dataset. The authors used the reconstruction accuracy of the vector-to-task model as a proxy for its training quality. To explore this, they trained multiple vector-to-task models with different numbers of epochs, resulting in varying levels of reconstruction accuracy. Then they evaluated how well the text generated by each model performs on downstream classification tasks. This design allows them to isolate the effect of vector-text model itself on the overall effectiveness of dataset distillation. The results reveal an important trade-off in training the vector-text model. When the model is undertrained, its reconstruction accuracy is low, and the generated text lacks enough semantic content for downstream tasks. On the other hand, an overtrained model tends to reproduce the original data too closely, which undermines the goal of information compression. The best performance was observed at intermediate levels of reconstruction accuracy, suggesting that there is an optimal training regime. In short, effective distillation requires a balance between fidelity and compression in the vector-text model. While this paper focuses on data efficiency, another common approach in NLP is parameter-efficient tuning, such as LoRa or low-rank adaptation. LoRa reduces the number of trainable parameters, while dataset distillation reduces the number of training data. This experiment asks, how do these two strategies compare in practice? To answer that, the authors used a T5-based model and tested three methods: full fine-tuning, LoRa, and the proposed distillation method. They compared these approaches based on two key metrics, accuracy and training time. The key findings from this comparison are as shows. In terms of accuracy, both LoRa and the proposed distillation method perform comparably across tasks. However, when it comes to training time, dataset distillation is significantly faster. While LoRa does reduce the number of trainable parameters, the overall training time doesn't decrease proportionally, mainly due to the data size and compute overhead. This highlights one of the core advantages of dataset distillation in practical training scenarios. In conclusion, LoRa and dataset distillation optimize different axes of efficiency. While LoRa reduces parameter count, dataset distillation uniquely reduces total training time, making it highly suitable for fast iteration settings. These results suggest that parameter-efficient and data-efficient methods are not mutually exclusive, but rather complementary in building scalable NLP systems. Based on these findings, let's now move on to the conclusion. To conclude, this paper presents a dataset distillation framework for text built on LLM-based embeddings. The method produces compact and human-readable datasets through a three-step process, including vector-text reconstruction. Experimental results demonstrate strong performance across various downstream models and tasks. Ablation studies also confirm the critical roles of embedding quality, task-specific prompts, and vector-text training. Compared to methods like LoRa, this approach achieves competitive accuracy while offering significantly faster training, making it a compelling option for efficient NLP systems. Despite the promising results, the paper has a few notable limitations. First, regarding task simplicity and evaluation, the main experiment is conducted on IMDb, a binary sentiment classification task. This task is relatively simple and with a baseline accuracy around 50%, making it hard to draw strong conclusions from small improvements. Additionally, even low-quality distilled data might contain keywords that skew results upward. The evaluation is also limited to classification, whereas modern LLMs are used for much broader tasks like question answering, summarization, or dialogue generation, which this study does not cover. Second, on the practical necessity of textual distillation, text data is already abundant and diverse. In many real-world cases, selecting high-quality subsets from existing corpora may be more practical than generating synthetic datasets through distillation. Another important limitation is the adaptability of the method to rapidly evolving LLM architectures. The embedding and vector-text models used in this study are based on relatively outdated architectures, such as T5 and early embedding APIs. It remains unclear whether the proposed framework can be effectively applied to newer models like GPT-4, Cloud, or Gemini. Unlike computer vision, where model backbones like ResNet or VIT remain stable for long periods, LLMs evolve rapidly, making it hard to develop long-term distillation strategies. As a result, efficiency methods should be designed with domain-specific dynamics in mind rather than assuming cross-domain transferability. That concludes my presentation. I'd like to open the floor for questions and discussion. Well, since my background is not specifically in large language models, I'd especially welcome any insights or perspectives from those with expertise in LLMs. Thank you for listening.
Okay, thank you so much for your clear presentation, Heeyeon. So, is there any questions from students? So, I have one more question about the methodology. So, I just wondering that after performing text distillation and the text reconstructed from the embedding, that embedding to text phase,
Yes.
that text is still human readable or it just have a random word or something?
Well, the paper said that it was human readable, but they didn't they didn't give the real how the real distilled data set looks like. So I'm not sure how much it is readable or not, but anyway, they said that it's readable.
Okay, thank you.
Excuse me, can you hear me?
Yes, I can hear you.
Oh, yeah, thanks for the presentation. And I also have a quick question about the methodology part. And in the text to embedding conversion, yeah, this part, um, is it utilized, or does it utilize multiple models to extract the embedding or just use a single model?
I think they use single models and they just did yeah, so they used a single model, and as we see in this table, they use the embeddings of each single model like 4 times for Glove once and E5 Face once and OpenAI once, like something like that. So in conclusion, they use a single model for making the embeddings.
Okay. So how how do they utilize the prompt to select the or to select the task specific embedding? I'm very curious about this step. Yeah.
Well, actually, in the paper, it just mentioned that they used the prompts for like some exact embeddings to make some exact embeddings, and they didn't exactly show how they used it. So I'm not sure about that. I'm sorry.
Yeah, because I see the main figure in this paper, and there is a template prompt. Yeah, could you go back to the slide? Yeah, this one.
Yes.
The task specific prompt. So I was wondering if they just utilize this prompt to rephrase the text and then extract the embedding from the rephrased text. Yeah, I don't know. Yeah.
Yeah, well, I think so, but well,
Okay, thanks.
Yeah, okay, thank you.
Yeah, because I also see I double check the paper. Yeah, they didn't tell any. Yeah, they didn't tell any details about that.
Yes,
Yeah.
right. They didn't provide any details. Anyway, thank you for your question.
Thank you. Yeah.
So is there any more question from students? I think there is no more questions, so we can wrap up our reading group session right from now. So thank you all for participating in this reading group session today. Thank you.
Thank you.